Paradox. Two doxes. Also, I didn't really mention, but I assume you guys noticed we have the media vision, right, the courseware, so take advantage of that. Everyone know about that? You know where to find it? Okay. All right. So the paradox was that, let me not address the paradox directly yet, but the basic thing that is funny, it should already appear funny to you, is that, okay, so if I go racing past you, I finally lose the 20 pounds I put on a few years ago, right? You'll see me as squashed. But then the weird thing is, it's equally valid if I said, I saw you guys race past, I'll see you as squashed this way. And it's the same, at the same time. I could be the one moving relative to the room, but neither one of us has a more valid viewpoint. You say I'm squashed, I say you're squashed. You say my clock is running slow, I say your clock is running slow. So this seems really odd. And when I derived the length contraction formula, which I did very simply after having done a little bit of algebra to get the time formula, I could have, by making what turns out to be the wrong argument, gotten the wrong answer because of the fact that sort of everything, both of us see, both situations like that. So, okay. All right, that's weird. And so I can't just give you a quick real answer to that without thinking a little bit harder. So let's consider another really simple situation that brings out immediately sort of the amazing thing about the speed of light being constant. Let's take a very simple idea. Anna, once again, is going to race along at V. She has two light bulbs out at the end of her hands, and at some time, bink, she turns them on. And Bob sits here and is going to watch. He's a little bit puzzled, scratching his head. Okay. Well, okay, what happens? Anna's racing by, she turns on the two light bulbs, and sometime later, time passes. There she is, the light bulbs. And the two photons, or two beams of light, just hit her. She's surprised. And they hit her at the same time, right? I mean, if I turn on two light switches, they hit her at the same time. Now, here's the amazing thing. What does Bob see? He sees her going along and emitting the two light bulbs, turning on the two light bulbs. But of course, the amazing thing about special relativity is he sees this light go at speed c and that light go at speed c in his frame. Speed of light is c for everybody. And so she's going, let's suppose she's going half the speed of light. So it is really weird. Because clearly, after the light is emitted, he sees her moving over and racing into that light. Okay? I mean, that's straightforward. He sees her moving over and racing away from that light. Incontrovertibly, right? Okay? For Anna, oh, why do I call it Anna? Gosh, so pretentious. The book calls her Anne. I never even noticed that. I started saying Anna. Oh, well. I don't know what's in my brain lately. On the left, it's just some distance over c. And on the right, it's some distance over c. Say her arms are length L long. I'm not going to do equations here. Just, clearly it's same length, same time. The time it took for the light to get there. But for Bob, time for Bob on the left, that's supposed to be an L, is greater than time for Anna on the left. because he saw Anna racing along before the light caught up. Time for Bob on the right is less than time for Anna on the right, because he saw the light go a different distance, a shorter distance. I mean, it's just as simple as that. And that has to be the case, given this bizarre thing, that the speed of light was the same for everybody. So what can that possibly mean? Suppose that it took 2 seconds up here. Anna saw it take 2 seconds. And let's just suppose, for the sake of argument, that this was 3 seconds and this was 1 second. Okay? That basically means that Bob has to conclude, Bob must, and then there's another key point. I mean, we're basically saying that the times are not lining up. That's really the only conclusion. They don't even agree on what time things happened. All right? What do they agree on? They have to agree, if Bob is sitting here watching the outcome, I guess he's still puzzled. But they have to agree on this, because this did happen. There was an instant in time when the two beams of light hit Anna's head. Okay? So that's one of the things we talk about in relativity. If you can find some simultaneous event that they can agree on, that's sort of incontrovertible, that's what you want to, anchor your thinking on. Clearly, if Bob sits here, and even better if they're lined up, when these beams of light hit, that you have to hold on to. They can agree that that was a time. There was a moment in time, there was a happening, if you will, where Bob and Anna and the two photons were all together in one spot. Okay? At least in one spot in X. So therefore, if I go back 2 seconds, again, let's assume that this is 2 seconds. Let's assume this is 2 seconds. Let's assume this is 1 second. Let's assume this is 3 seconds. If I run Bob's clock back 2 seconds, what does he see? 2 seconds before this, Bob's sitting here. This light was going to take 3 seconds to get there. It's 2 seconds earlier. It's already been traveling for a second. He sees Anna at some present time, at the moment. He sees Anna's right hand 1 second into the future. On the right, on Anna's right, on our right, over here, that photon is going to take only a second to get there. This is 2 seconds ago. It hasn't left yet. He's seen into the past over here. Yeah?
What is the time, 3 seconds and 1 second?
Sorry. I argued that good question. I argued for Bob that this light will take less time on the right and more time on the left. And I just made up some numbers to illustrate the point. Suppose it takes 3 seconds on the left because Anna's racing away from the light, and 1 second on the right because Anna is racing into the light. Okay? Yeah?
Both frames of reference agree that
No. Sorry, don't mean to shove down your throat. They don't. Finish your thought, sorry.
but they do agree that they both arrived at Anna at the same time.
They don't, yeah, sorry, you're right. See, they have to agree that they arrived at Anna at the same time because that really happened. I mean, that really did happen. I mean, things are getting topsy-turvy here. I could probably tell you, there's pink elephants, and and you'd say, okay, now there's pink elephants. No, okay. There are some things that really happened. The light really hit Anna's head. And the two let's think of Anna's head as a point. The two photons hit that point. That happened. So then we have to work backwards. And what we have to conclude is that they didn't leave at the same time, according to the both of them. Okay? Everyone happy? All right. So now, given that we're in this situation, it turns out that it's not often this happens, but sometimes this happens. It's going to be easier, actually, if we just simply get a little more mathematical. Believe it or not. So I'm going to spend the next 10 minutes or more just doing algebra, and I'm going to derive something. And bear with me. The book actually skips a couple of steps, but I think it's worth just doing it. the point is, one of the reasons I want to do it is this really is the heart of special relativity, and it's really not much. And you're going to be working on homework problems that are about as complicated. And we're going to do a little bit of algebra. And when we're done, I'm going to re-examine these sorts of things. And now I'm going to be able to say, I'm going to be able to talk about this again, but I'm going to be able to write down equations, which actually, once you start, once you understand and once you start to do your homework, I think they're going to help and explain what's going on. Okay? So let me do that. I mean, what did we just conclude? We just concluded that basically that time is relative and length is relative. They're changing for the two. I think this is mine. For the two of them. So the way we talk about that is we'll say there's a frame of reference, which is Bob's frame of reference. Okay, if you will. I'm not going to draw Bob anymore. Not right now, anyway. I'll come back to drawing Bob again. Okay, and just by convention, I'm going to say that's the XYZ frame. I'll label it frame S, and then I'll say another frame is whizzing by, just like Anna was doing. So this is Anna's frame. And I'll call it the prime frame. It has a velocity v relative to this frame. And hopefully what is straightforward is that in y and z, nothing fancy happens, okay? But in x, we have this translation and this speed. And the point is that they're not going to agree sort of on distances anymore. In other words, the distance, the location along this in this axis of x prime somehow might depend on x and t. It might be some function. Okay? And similarly, the time, this is what I just argued, time might, in one frame, might depend on the position and the time in another frame in some weird way. So this is the most general way we would think about it. And it turns out things are actually related in a linear way. You'd always like to try a linear way. It's the simplest way to write equations if you can. So let's just try it. Okay? In other words, I'm going to say that the position in the moving frame in Anna's rocket ship, and I just mean like, the normal x-axis you guys are used to using, the value of it will be related to whatever Bob is measuring, but depending on when Bob measured it. And it will just be some linear coefficient A and some linear coefficient B, similarly for time. Well, let me make the ansatz, let me just assume that that's going to work out to somehow make sense of all this. Okay? So now let me erase this. And let's consider a few cases and try to figure out, well, we will figure out what those coefficients, A, B, I didn't write down C, because C, the speed of light, is going to enter in. So A, B, D, and E are. All right? So let's just think of a couple simple things. First off, let's do an object at x prime equals 0, okay? Just sitting there. Okay? So if I have an object at x prime equals 0, what's x? I mean, I'm just saying it's an object at rest at Anna's origin. And not to get involved in fine and subtle things, I'll just say, look, it started at t equals 0, t prime equals 0, both x's lined up at 0. That's implicit in what I'm saying. Okay, so everybody started not at rest, but they happened to line up at t equals 0, the origins lined up, they both said the clocks are equal to 0. Okay? So then x equals vt. Right? That's simple, right? It's just, I'm watching, and Bob's just watching a thing move past. Yeah? Huh? Sorry. I implied that when I said it's at x prime equals 0, and I meant it's at x prime equals 0 forever. But yeah, so it's at rest in the S prime frame. Yeah.
Isn't S prime the moving reference frame?
Do what?
Isn't S prime the moving reference frame? So
S prime is the moving frame, but I can certainly have something at rest in that frame. I'm now Anna. I'm walking along. The chalk's at rest. What's the position of the chalk as far as you guys are concerned? V times t, right? Assuming we both agree that it started at x equals 0 at t equals 0. Okay, straightforward. All right, so if that's the case, x equals vt, x prime equals 0 equals, I'm going to now use these two equations. X prime equals 0 equals ax plus bt. And x was equal to vt plus bt. Okay? So if 0 equals avt plus bt, t cancels out, and b equals minus v times a. So I already have a relationship that has to be true. Okay? Now let's consider something else very simple. An object at rest in S, and x equals 0. And it's just sitting there. Okay? So I go cruising past the Coke can, x equals 0, x prime equals 0, at t equals 0, at t prime equals 0, and I watch the Coke can move away from me. Okay? Clearly, x prime for the Coke can is minus vt prime. In my frame, it's just moving backwards, velocity v, x equals vt. I'm just moving along with v. Okay? And let's try to plug that in. Well, again, I'll use this top equation. And I have no, let me be a little bit clever. Instead of plugging in like that, let me divide the two equations. This will save a line of algebra. It's often a useful technique. Divide the two equations. Okay? Now x prime over t prime is equal to minus v. Okay? And then x was 0. I just said, look, it's sitting at the origin. So this is 0. And this is bt over et. Okay? So therefore, b equals minus ve. But I also had that this was equal to minus va from above. Okay? So E equals A. You don't really need to copy this down. This is done in the book, right? But I want to do it. I just want to do it because this is really straightforward. It's simple, a little bit of tedium, and we're going to get a really profound result. Okay? Now, this didn't say anything about relativity. Not yet. This would be true before relativity if I were trying to sort of in a fancy way work out the Galilean transformation equations. These are called the transformation equations. How does my position in time, if I'm running past you, relate to your position in time? Okay? But now let's add relativity. Let's suppose as I shoot past the Coke can, I turn on a beam of light. And let's, okay, or better yet, as I go past the Coke can, we have some little sensor system and bink, light goes off for me and the little Coke can, okay? Or just a light bulb here. It doesn't really matter where the light bulb was. Here's the bizarre thing. As I go racing along, I see that light going at a speed c relative to me, and you guys see the light going along as a speed c relative to you. Okay, so 3 is a light bulb. Light starts at x equals x prime equals 0, and t equals t prime equals 0. And so what we know is that x equals ct, and x prime equals ct prime. So that's the bizarre thing. We both see the light, even though I'm racing past you, with the same equation. Okay? Once again, I want to play the trick of dividing. It'll make things easier. Well, you see this? I wrote x prime over t prime equals this stuff. If I divide this part by x and I divide this part by x, can't you see that this is x prime over t prime equals a? No, sorry. I want to divide this by t, the top by t, the bottom by t, and that's a x over t plus b over d x over t plus e. Now x prime over t prime is just the speed of light, distance over time. And that's the speed of light, and that's the speed of light. So this is a c plus b over dc plus e. All right? But then I also had these relationships. I'm going to eliminate a and I'm going to eliminate b and e. So c equals ac plus what's b? It's minus va minus av. And the denominator is d, which I don't have an expression for yet, plus e is a. Okay? Multiplying through by the denominator, I have dc squared plus ac equals ac minus av. All right? And ac canceled. And so then I have d equals minus v over c squared a. Again, this is in your book with some algebra lines skipped. So there, that's it. And that's what I first want to do. And let me stop and appraise. So I have d, e, and b in terms of a. So let me take the basic equation and I write x prime equals a x. For b, I have it's minus va. So minus v times t. Right, that's just plugging in the b term in the original equation. And t prime, I have d. Well, it's in terms of a, and then I have minus v over c squared x. And e was just equal to a. Okay? Now, it turns out at this point I have to do one more thing to get rid of a, and then I'll have my then I will have written down the meat of special relativity. I've done it. I want to consider the opposite equation. Physically, I want to think of this is an equation. Let's give it a second. I did a lot of algebra. Let me explain a second then what this is. This is a formula. I don't know what A is yet, but ignoring that, this is a formula where in Anna's frame, my frame, I'm going to be Anna from now on, right? I'm going to have to figure out how to deal with that. As I'm racing past you, these are relationships that would tell us I mean, you know, we saw that this is getting topsy-turvy in terms of whose time and whose distance. If we say that the Coke bottle is at x equals 0 and some time, this will tell me where on my coordinate axis the Coke bottle is. And similarly, if we talk about some event into class that happened at some time or some x, we'll know what time it was that I measured. Okay? So this is my understanding of you guys, okay? Or maybe a little bit differently. as I'm running wrong and I have this coordinate system on me, you guys could look at it and you say, well, this is where it is for us, and that's the value you'll read off on my coordinate system, okay? And that's the time you'll see. This is the equation that explains the light bulbs, and we'll come back and we'll look at it again, right? But this equation is going to say that at some time you have, for larger x, you're looking in the past, and for negative x, you're looking in the future. And that was what I argued was going on. That was the answer to that conundrum with the two light bulbs going off. Okay, so that's the power of these equations. Okay, so now it's useful just to simply invert them. Instead of getting x prime and t prime in terms of x and t, let's just do the opposite. Okay, that's just a little bit of algebra. So let me first start to invert this equation just by sort of unwrapping it. I'll divide by a and rearrange. I'll say x equals 1 over a x prime. So I just divided by a, and I'm flipping left and right. And then I'll put the vt along with the x prime. Okay, that's good. I got x now in terms of x prime, but I want to get rid of t. So let me solve that for t. T, again, I'll divide by a, 1 over a t prime, and then I'll put this term over there, plus v over c squared x. Okay, and now I'll plug that back in there and write it out. So x equals 1 over a x prime plus v times t. I won't put the parentheses. It's v times t, which is v times 1 over a t prime plus v times this term plus v squared over c squared x. That's good. I've got x here and x there, and I've got what I want, an x prime and a t prime here. If I pull this thing onto this side, you can see this. This is 1 minus v squared over c squared. And on the right side, I have 1 over a times x prime plus vt prime. Okay? It's hard to walk back and forth. I'll write that down. I can similarly do algebra, and I can find, if I plug this expression into here, I can similarly find an expression for t. Okay? Oh, sorry, I haven't finished yet. Okay. Well, I can similarly find an expression for t. And I'm not going to copy all the algebra back over there. If you think about it, the next step for the x equation gets me to this. It gets me to x prime plus vt. And I'll skip the algebra. But similarly, if I solve for t, the algebra works out almost the same, except I get that. Kind of ugly, but straightforward, right? Straightforward. I had that x prime is 1 over a x minus vt. Right? That was the thing. That was what I solved here. That was the first thing I got. Similarly, I had the t prime, and I'm just copying down from the top right, is 1 over a minus v over c squared x prime, no x, this is t prime, x plus t. So let's look at these two equations. Actually, something should have come out. Notice this expression, the coefficient's different, but this thing and this thing are almost the same. There's just a negative sign. Well, actually, there had to be. If I'm going to, yeah, go ahead.
It's A over there and then over A.
Well, no, right. It's, thank you. Not 1 over A. This is A. Thank you. Apologies. These two expressions had to come out about the same, right? And when I go racing past you, and we consider you guys to be the unprimed system and me to be the prime system, you see me moving with a positive x defined, with x defined in the normal way, to your right. But I can just say, again, I'm at rest and you guys are racing, so I should have the same equation, except you're not going so I'm going towards positive x for you, okay? But my expression for you, you're going the other way. These expressions ought to be the same, except with a minus sign reversal between v in the one case and v in the other case. Okay? That has to be the case. Therefore, this coefficient, this whole mess with the 1 over a and that thing, has to equal a. You happy with this last explanation? Okay? So this is simple. 1 over a times 1 minus v squared over c squared has to equal a. Okay, I can multiply by a on both sides. Therefore, a is the square root of 1 minus v over c squared, v squared over c squared. And that's equal to gamma, the term we derived last time. So gamma comes back in. So in fact, I don't want to rewrite all this stuff. Well, I do, just to make it compact. X, be very clear about this. It's gamma x prime plus vt prime, no, minus vt prime. T is gamma, I'm sorry, I'm writing that one. That one's a plus. These are the equations. These are the equations. This was what I worked to. In fact, I got these on top and these on the bottom, but these are the ones you usually write down first. That's just convention. Both are equally valid. Okay? Both are equally valid. But we're often asking the question this way. You guys are there, you're working in your lab or hanging out in your house or whatever you do, okay? And I go racing past you, and your question is, what's going on in my frame? X prime is what's going in my frame. You look in your frame at some x, at some time. This is what's going on in my frame. This is what the answer is in my frame. You look at some point in time, in some place in your frame, and some time in your frame, and this is the time in my frame. Before now, I could imagine there was a transformation equation for x. But I would never have thought there was a transformation equation for t, right? We agree on the same time, but now we now no longer do. Notice that if the gamma is 1, the top equation is simple. If I'm going racing past you, and there's some point in your frame, it's going backwards for me. That's the negative sign. You know, just as I go along, the Coke can is just going to, you know, my measurement of the Coke can is just minus VT. So that part of the equation is completely straightforward. It's just the gamma. The gamma contains all the special relativity physics. But the time equation is just more bizarre. You agree with me if v is 0, which makes gamma equal to 1. Okay, time is time. But if I'm moving, okay, my time, t prime, the time you see in my frame, looking at some place in your frame, you know, I'm racing by, you see, let's try this again. I'm racing by, pick a point, X. Let's say X equals 0 where the Coke can is. Okay? You see, let's say we agree that this is T equals 0. However, I'm carrying a frame along with me. I'm carrying a javelin. You look at the back of the javelin at some place, X, that might be negative. Then you add this, the negative sign, you add this term. You see into the future at the back of my javelin. Okay? If you look at the front of my javelin with a larger X, you see into the past. Okay? So we don't agree on the simultaneity of frames. When I go racing past you or you go racing past me, I can't look. Literally, when I watch you guys race past, you guys will be in the past and you guys will be in the future. I just can't take a snapshot of you guys at one time. Okay? That's what's going on. How's that? Everything okay? Okay, so let's return to our earlier cases. And let's just get practice working a problem and using these equations. So I started out the class with, I started out this yesterday, or Wednesday. We derived the time. We derived time dilation by having me, Anna, race past you and shoot light up and down. Okay? And we analyzed that sort of carefully, drawing triangles and whatnot. And we derived the time equation, time dilation. Let's use these formulas. Oh, okay, and sorry, I forgot to mention, do you know the name of these? If you've read in the book? Lorentz Transformations. Lorentz was a mathematician who was contemporary of Einstein. I believe he actually came up with these things earlier, but he was sort of more working kind of almost as a mathematical curiosity. He couldn't believe this was describing reality. And Einstein sort of put this together with the Michelson-Morley experiment to do all this. Okay, so we're going to use the Lorentz transformations to examine that. It's really pretty simple. Here's Anna in her rocket ship going past Bob. And Bob is going to watch a clock on Anna. We don't even have to talk about the light bouncing anymore. Anyway, if it did, the light was moving up and down in y, and y is the same for both of them. We'll just simply say, let's pick a clock at, this is careful here, at x prime equals 0, fixed. In other words, we're going to have Bob just look at a watch just stuck in Anna's frame. And I look at these four equations and I think what to do. I'll just pick x prime equals 0 and that it stays there. For any of these equations, I can think of a change. So I can take this equation, I'll take this one, and I can write down delta t. Not just t, but I could think of applying it at two different times and taking the difference. But in this situation, I picked this equation because what I did is I said it's fixed in Anna's frame. And this is actually the work in working these problems often. It's just identifying which of these equations do I want to use. I said let's look at a fixed watch at a watch sitting at rest in Anna's frame. X prime delta x prime is 0. And so that's it. Delta t equals gamma delta t prime. That's the same statement that I made on Wednesday, but slightly different, just notation. I'm saying the time change Bob measures is bigger than the time change Anna measures. And that's the statement that Anna's clock is running slow. It's not really running slow for Anna. It's that as Bob watches Anna move along in space, he sees the clock moving differently in time. But it's not kind of smoke and mirrors. Again, it is profound. As I said, if he can sit at one spot and watch Anna age, she will not have aged in Bob's frame, literally. I talked about the particles that hit the top of the atmosphere that only live 2 microseconds on average. By the way, you'll measure that 2 microseconds if you take junior lab here, 2.2 microseconds. They wouldn't reach the surface of the Earth at the speed of light if they didn't have an extended lifetime from this effect, and yet they do. Okay? So it's a real thing. I could have applied it the other way. Does Anna see Bob running slow? Yes. But I've got to be careful which equation I apply. For instance, I could say delta t equals gamma delta t prime. So therefore, I say something like delta t prime equals 1 over gamma delta t. This is the conundrum I was doing in a different form. I might think, oh, well, does Bob see Anna run slow? This says Bob sees Anna run slow. This says the opposite. This would say Bob sees let me not write that down. What I'm trying to do is say, this is Bob sees Anna run slow. But I've got to be careful about which way I apply that. It only worked because I picked delta x prime 0. I can't sit there and like take a point here and a point here and compare them. I'll run into confusion like I just did. Okay? And I'll come back to that. But if Anna wants to watch Bob, how would I apply it? I mean, that's really what I was just trying to say. The way Anna would want to watch Bob is not with this equation. In this equation, if Anna watches Bob go by, Bob doesn't sit at one value of x prime, right? So you would have to solve this. You could use this equation to figure out what's going on. But if I said t equals 0 and t prime equals 0, and now I get a delta t and a delta t prime sometime later, I would also have to account for the fact that in Anna's frame, my frame, the Coke can has moved backwards. All right? So if I want to say how does Anna see Bob, I say let's pick a fixed point in Bob's frame where x won't change. And then I apply the equation again. And then I get the other conclusion, t prime, delta t prime is gamma delta t, which is the opposite of this equation. That's how they both see the other as running slow. But they have to each observe a fixed point in the other frame. There isn't really a meaning for me asking you, I see you guys running slow as you run past, but I can't really talk about all of you running slow, right? Because you guys are in the past and you guys are in the future as you guys go past me. So it gets kind of confusing. But just be careful about applying the equations and you get to the right place. So let's do the length. All right? We had this same situation. And we'll say that Anna has a length of the spaceship which she measures. If she's at rest in the spaceship, we'll call that the proper length. We're not going to agree on the length anymore, Bob and Anna. Whoever's at rest gets to say that's the proper length. Similarly, there's a proper time. Anna says, I have the proper time. If Anna goes, if I go racing past you and I measure some time, that's the proper time in my frame. That's the lifetime of the muon. If someone else measures as the muon races by, they measure in a bigger time. Okay? So for length, we have a situation where as this race is past, and Bob's here and is going to measure it, okay? The initial situation is here. This chalk is gone. I'd have x equals 0, t equals 0. And let's say this is the prime frame. I would have, this is initial. X prime initial would equal L0. This would be 0 in the frame, and this is L0 in the frame, out at the end of the rocket. And T initial prime equals 0. Okay? The final situation would be, this is moved past to here. Bob is still sitting at 0. And then some delta t has happened. The final x prime in Anna's frame is 0. And t final equals delta t prime. Okay? So I just have those conditions and I want to plug in. In other words, delta x was 0 in Bob's frame. So if I look at these, well, I want to get an answer with x. I can use this equation here, where delta x is 0. Okay? And I'll write delta t prime equals gamma minus v over c squared delta x plus delta t. Delta x, 0 and initial and final are the same. Delta t prime is delta t prime and delta t. Well, the way I thought about this before is as the rocket ship passes, the time is the length divided by the velocity. In Bob's frame, it's some length. In Anna's frame, it's the proper length. Okay? So delta t prime here is L0 over V. This is equal to gamma, that term's 0. Delta t there is L over V. And I get that L is 1 over gamma L0. So that's what I derived before. I chose one of these equations and used it. I could have chosen other equations, but there was no ambiguity. There was no guessing as to do I consider Bob to think about Anna's time? Do I think about Anna to consider Bob's time? Okay? I just wrote down initial and final x's and t's and proceeded. All right? And I get an answer. And no matter which way I try to work with these equations, I'm always going to get the same answer. I'm not going to get something ambiguous. The way I asked you about the conundrum was, well, doesn't Bob think that Anna is running slow? Doesn't Anna think that Bob's running slow? And doesn't Bob think that Anna's running slow? Which way should I get a time equation to try to solve this? And the answer is, I had to pick a time where Bob is sitting at, because Bob is at one place, I had to say Anna considers Bob's clock to run slow. I couldn't say Bob considers Anna's clock to run slow because it was the front of Anna's spaceship that first passed, and then it was the back of Anna's spaceship that passed. And as we see, the time that Bob sees in Anna's frame, this is the time in Anna's frame that Bob measures, depends on on where it was. That was why I couldn't apply the wrong version of time dilation to do the simple derivation. I had carefully picked the right one without thinking hard, and I got the right answer. I can't say Bob looks at this time and then that time and looks at a difference because there's this spatial dependence of the time. Okay? And so that's the solution to the conundrum. See you guys Monday. weird. As you guys go past, or no, since you're watching me, let me do it this way. I'll go past you. You guys are S. I'm S prime. Let's just look at the math first, and then we'll talk about it. The math says this is T prime. Pick x equals 0 at the coke.
Okay.
Over here is negative x.
Yes.
Over there is positive x.
Yes.
Okay? Let me say that when I pass the coke, t equals 0 and t prime equals 0. I can